Hey everyone,
Good morning.
good morning. How are you guys?
Good morning.
Hey, Leck.
Hey Laurie. Laurie, may I make you a co-host so that you keep admitting people while I'm introducing our speaker today?
Okay, sure. Hey, good luck, Dylan.
Thank you.
It's your big day, isn't it?
Yeah, finally. Overdue.
Okay. Keep adding people, and I cannot find Laurie in this.
Sorry about me, Leck. Just keep adding people. I'm
Okay.
doing a good job without me.
We'll say that's a nice Tim Tams mug.
Yes, Tim Tams.
Yeah.
If anyone ever gets to Australia, you got to go for the Tim Tams. They're good.
There we go. I've seen them occasionally in the US.
Yeah,
Randomly.
you can get them. You can get a couple of the flavors.
Yeah. None of the really fun ones.
No. In
No.
Australia, they kind of change them up. I mean, they have the basic sort of, regulars, but they change them up all the time. Yeah, we were having some mango and something a little while ago, and they were pretty cool.
Nice.
Yes, cherry ripes. They make a good Tim Tam as well.
Ooh, that sounds super tasty.
Yeah, no, they've got some good combos. Yeah, I imagine your dad's been snacking on a few of those.
Probably. We're on the X brand version, more likely.
Looks like I cannot make you co-host from here. This is strange.
Oh, look, Lex, to be honest with you, I don't want to be a co-host.
Well,
I don't want that responsibility.
Because I'm a substitute host for this one, anyways.
All right.
Wait, Dylan, do you have another light in there?
What's that?
Do you have another light in there or something?
No, it's super.
Yeah, your face is real dark.
I know. Yeah, I'm trying to. Maybe if I tilt the camera down a little bit, does that help at all?
A little bit.
Okay. Yeah, it's either this or the lights just turn off. I've had to get so many presentations where I look like a silhouette just because my webcam is awful.
You're one of those two-dimensional people.
So
Yeah.
I see that John is in here. John, if you can, from your position, make Laurie.
To make Dylan a co-host, I hope this is going to be okay because we'll see.
Because I cannot,
internet
from my vantage point, I cannot do that. So we'll wait another 4 minutes before we start to give everybody a chance to join, and then I will introduce our speaker for today.
I love your background.
I'm substituting for John Simonson today, who is in a place with poor connection, so he could not possibly be sure that he can get you through this thing in one piece. But we are happy to have him with us. Anyways. It's my spring background.
Like Kenneth's background, he looks like he's down at the swimming pool doing a few laps.
Yeah. How is everybody doing?
I'm doing good.
Very good. Thumbs up. I see one. I wonder how many we can get here.
Yeah, so it looks like we have 32 people now. I also opened up the waiting room since I'm co-host, and I'm also admitting people as I see them pop up.
Oh, super.
Yes.
Very good. This is why I don't see the people scrambling for admission any longer.
Okay.
Good. All looks fine. We'll be ready to start in a second. Two more minutes. use the time to stretch, refill your tea.
Get a Tim Tam. That's what I'd do if I had any.
Okay, yes, of course.
We don't have any here, so we're stuck with drinking out of a Tim Tam cup.
Okay. I think the number of attendants is like at stable level right now. 32 people is pretty good. Pretty good turnout. Sorry, a knot on my tongue. Welcome everyone to our weekly graduate seminar. I'm substituting for John Simonsen, who's currently in a place with rather whimsy internet connection and could not host this gathering in reliable manner. Today's speaker is Dylan Willard, who's been with us for 2-3 years, right?
2 years, a little bit less than 2 years.
A little bit less than 2 years. Oh, time flies, but my sense of time in COVID has been down the drain completely. I mean, things are, I cannot measure time properly any longer. So from the little survey that John performs with our speakers, I know that Dylan was born in Lexington, North Carolina, but he grew up in Oregon.
I grew up in Lexington, North Carolina.
Oh, so your response to whether you grew up here was yes. So here, apparently,
I thought it was the question after, where were you born? Did you grow up here? So I was saying, yes, I did grow up in Lexington.
Sorry.
Okay, so we need to fix this survey because it does not very good. He earned his bachelor's degree at Virginia Tech in the program of sustainable biomaterials, and has already accepted the job at Hexion in Springfield, Oregon, as a technical sales representative, which is very nice to have a job secured, ahead of your graduation. Congratulations.
Yes. Thank you.
In terms of hobbies, apparently he likes to do everything that has some board in it, right? So this is this kind of like wood science bias. It's like surfing, snowboarding, and skateboarding. With this, I'll leave the floor for Dylan and let him present his research project.
All right. Thank you, Lek. So I will pull up my PowerPoint very quickly. Let me share my screen. This is very exciting. This is the first time I have given a live presentation in a very long time. So I've been used to just recording videos and then putting those up for people to watch, and you get to do a bunch of retries. So this will be fun. Can everyone?
Just so that everybody knows, we are recording this session as well. We'll be handling questions and answers at the end of the talk.
Yes. Can everybody see my screen okay? It's full screen on the PowerPoint for everybody? Okay. Sounds good. All right. Then I will go ahead and get started. So my project is the analysis of adhesive atomization on composite bond performance. I myself am working on this project, of course, and some of you all may remember the visiting student, Tomas. He also began this project. And the personal investigators on this project are Dr. Fred Kampke and Dr. John Nairn. So, and just a little heads up, I might jump out of my seat halfway through this presentation because I'm in my office and the lights are on motion sensors. And I feel like every time I do some kind of a presentation or conference after 30 minutes, I have to jump up and make sure my lights come back on. So let's go ahead and get started. The objectives of this project are to establish guidelines for the atomization of resin for a wood strand composite. Specifically, the objectives are to determine the optimum droplet size for aspen and southern yellow pine, the effect of adhesive viscosity on droplet size, and the effect of spinning disk atomizer RPM on resin distribution. So, and I will give you all a little bit of an outline for what we'll be going over in this project. There are 4 main components. the characterization of our phenol formaldehyde resin, which we are using in our project. I will elaborate more on that. We are doing two main types of mechanical testing, one which is veneer lap shear testing, and the second which is testing of strand board, which we are making in our lab. And the fourth section of this presentation, I will be discussing the image analysis of the adhesive droplets on our wood strands for this project. So the objective of our phenol formaldehyde resin characterization is to determine the differences of our resin. We are using 3 different adhesives for this project. The first adhesive, well, let me start by explaining that we initially got our phenol formaldehyde adhesive for this project from Arcland down in Springfield. They do not specifically manufacture OSB phenol formaldehyde resin in Springfield. They manufacture PF resin for plywood and LVL, if I'm not mistaken. And just a heads up, I might refer to phenol formaldehyde as PF, so just so you all know. So, and to determine the different characteristics of our phenol formaldehyde resin, we examine the viscosity, the tensiometry, and we analyze the molecular weight of our adhesive. And we are using 3 different molecular weights of adhesive for our project, which I will elaborate on in a further slide. So the first test that we do for analyzing the characterization of our PF resin is to analyze the surface tension. We do this using a tensiometer. It takes a live image and it is able to calculate the dynamic surface tension of our adhesive. As you can see in the photo on the left side of the screen, at the bottom right corner, that is actually the tensiometer itself. You can see the backlight and the camera, and that black box in the middle is actually where the PF droplet is suspended. If you remember in the previous slide, this photo is actually a photo taken from the tensiometer, and you can see the blue lines is actually going around the outside of the droplet, and that's what's calculating the surface tension based on the density based on the density of the liquid itself. So, and as you can see in the photo, there is a black box where the droplet is being suspended into. This is actually an environmentally controlled chamber. The tensiometer is actually hooked up to a water bath, which can control the air temperature within the box, which allows us to check the surface tension at different temperatures. So this is very important because a very big part of this project is keeping our resin temperature consistent, because with elevated or decreased temperatures, you can experience a lot of different resin properties. So we wanted to check the tensiometry of the adhesive over a wide variety of temperatures. So as you can see in the graph on the right side of the screen, we tested the tensiometry over a range of 10 degrees C to 40 degrees C. And we did not see a significant drop in the actual tensiometry or the surface tension, only about 1 millinewton meter. So that was not significant. We're actually going to go back and repeat this test with not all of our adhesives, because one thing we have ran into issue with is taking the tensiometry at elevated molecular weights and viscosities because of the size of the pipette tip that we have to suspend the droplets. Once we get up to the higher molecular weights with higher viscosities, it's hard for the adhesive to be sucked into the pipette and then suspended out to do the surface tension analysis. So we're going to go back and do this over a range of lower molecular weights and viscosities. So the second test that we do to analyze characteristics of our PF is we do a temperature versus viscosity test. This is very simple. We have a water bath, which we use to heat our resin or cool our resin. It can do both. And then we have a spinning disc viscometer, which we can use to suspend into the resin, and it can measure the viscosity. And as you can see on the right side where the graph is, the viscosity between our first and second resin for this project was significantly different. The main objective of these 2 resins was for them to have significant difference, of course, but we are testing them at 25 degrees C. So our target for the second resin was to hit 1,000 centipoise, which we were able to do. And the first resin, we actually did not advance at all. This was how it came from Arclin itself. So, and how we advance the resin is we allow it to sit at elevated temperatures in a water bath for a certain period of time. And we constantly monitor the viscosity. And once it's reached the desired viscosity, we pull it out of the water bath and we end up putting it in a cold room for it to stabilize. So then we can go back and use it at this elevated viscosity when we need to test. So for our third resin that we'll be using for this project, because like I said, we'll be using 3 resins. Initially, we wanted to have a viscosity of 2,000 centipoise, but since testing with the resin that we matured to a 2,000 centipoise viscosity, we found that it was actually too viscous for the atomizer to handle. One of the important parts about this project is consistency. And when using an atomizer, you want to be able to have a certain rate of flow for the adhesive through the lines. But after time, this resin was actually starting to clog up the atomizer, and we couldn't maintain a consistent flow of adhesive through the atomizer lines. So because of that, we had to reevaluate. And for the third resin, we are going to aim for a 500 centipoise viscosity resin at 25 degrees C. So the final part of our resin characterization is analyzing the molecular weight. We do not do this here at OSU. Like I said previously, my resin is from Arclin, so we are actually able to take samples down to Springfield for them to analyze a gel, or to do gel permeation chromatography tests and analyze the molecular weight and the molecular weight distribution, so we can understand how this also has an effect on the adhesive performance on the bond line. So as you can see, resin 1 and resin 2 are on the screen. I actually recently this morning received my email from Arclin analyzing the third molecular weight of the resin, but I didn't want to rush and try to put this in and reformat everything. So we've already made the third resin and started the test. We're currently in the process. So stick around for my defense if you're interested to see the next steps of this project with the third resin. So now I'm going to get into the mechanical testing part of this project. So the first method of mechanical testing that I'm going to describe is going to be our lap shear test. And we did this according to ASTM D2339. So, and it's very simple. We overlap 2 veneers that we make, which I will get into the process of how we make in the next slide. And we pull them apart, very simple as that, using the Instron downstairs. So, and I'll describe the different methods that we use. We do 2 different species of wood. We are testing on southern yellow pine and aspen. I'll bring that up again. We are doing southern yellow pine and aspen for all parts of this project. And this is because those are 2 common woods that are used to make OSB across the nation, but it differentiates depending on location. For example, the OSB strands that we acquired for this project, which are aspen, came from the Midwest, and the southern yellow pine came from Alabama, I believe. So, and in those different regional areas, that's the products that they're making OSB with. So we wanted to be able to do tests on both species to have relevant information for all industry members. So to create our lap shear specimens, like I said, we sourced our aspen and southern yellow pine from vendors in North America, which was Louisiana Pacific. We sourced these from a plant in Michigan and Alabama. And whenever we ordered strands, we specifically requested that they could send us some logs as well, so we can make individual veneers. This was because when planning on doing lap shear tests, we realized there might be a lot of variability with trying just to take 2 OSB strands and sandwich them together because they're very ununiform. But by making our own veneer, we were able to cut out a lot of the variability and have a very consistent piece of veneer in size and grain orientation. So this helped us to have hopefully some more consistent results. So how we made these from just plain Jane logs, we cut these logs into 1-foot sections and quartered them. We soaked them overnight, or at least for 24 hours in a heated tub. I was about to call it a hot tub, but we don't have one of those. And then we were able to use the radial veneer slicer down at Oak Creek to cut off sections that were probably about 1 foot long by 6 inches wide. And from there, we were able to cut out these 1 by 2 inch little pieces of veneer. And to make sure that the surface quality was consistent on all of them, we oven dried these with weights on top of them so they would flatten out. And we also used a hand planer and a wood scraper to level out the surface quality. One of the issues with something like Southern Yellow Pine, when you cut a completely saturated veneer and you have a 1/8 of an inch thin slice, once it dries, as we all know from being wood scientists, there's going to be different dimensional shrinkage between the early wood and the late wood. So we could tend to get some ribs in the Southern Yellow Pine that would stick up further than the early wood where the late wood was. And this can affect the bonding performance since we don't have a completely flat surface. So, and then to make these, or to actually get to making our lap shear specimens, first we had to spray some adhesive on them. We used this, or we did this by using a custom blender door for our OSB blender here in 191. If you all have been there and seen our OSB blender, we have a custom door that can fit on the front. This is a pneumatic sliding door. You can see in the photo, it has 4 exposed areas where you can put OSB strands specifically for these little veneers that we cut out to fit in there, and you can spray a 1 by 1 inch area. And the important part about this is that we can do it for a controlled period of time. It was very difficult to kind of plan how we were going to spray individual veneers, because once you're first starting up the atomizer, it's not going to have exactly the same spray pattern as it will once it gets up to speed. So with this device, we can run the atomizer for a little bit, allow it to get up to speed, spinning at a consistent 7,000, 10,000, or 13,000 RPMs, which are the speeds of the atomizer that we use. And then you can turn on the resin pump line. And once the resin is spraying out, you can then open the doors and get a controlled, even spray for a certain amount of time. We initially did 30 seconds, but after further examination, we realized that that absolutely caked the strands. So we moved it down to 10 seconds. And that was a very similar resin distribution that we saw from our OSB strands from the blender, which I will get into in a further section. So, and as you can see on the slide, I said that 3 wooden strands and 1 aluminum strand. So one of the difficult parts about this project, there's a lot of variation. You're not always going to get a perfect spray with the atomizer, and you can get some inconsistencies sometimes. So we put 3 strands on this pneumatic sliding door, 2 of them for the lap shear test, 1 of them to do an image analysis on. And then we also put a strand of aluminum in there. This strand of aluminum is so that we can remove it after the testing, and we can actually see the estimated weight of resin that we are expecting that's falling on the rest of the strands. So we weigh it before testing, we weigh it afterwards, and we can get an idea of the weight of adhesive that's on the strands. And we were going to initially do this with wood, but the way that we secure the wood strands to this door is that we tape them to the slide. But once you remove the tape can sometimes pull off some of the fiber on the back of the strands, which in turn sometimes can be a lot more weight than actually the amount of adhesive that fell onto the strands themselves. So this is just a better way to get more accurate results. So after we've sprayed our strands, we get ready to overlap them for lap shear testing. Like I previously said, this is in accordance with ASTM D2339. In the top left corner, you can see a little AutoCAD drawing that I made that gives a rough idea of, in a perfect world, what these would look like. It is 2 overlap strands with the 1 by 1 inch area, and on the ends it has 1 inch spacers to even out the shear of the bond line whenever we actually put it into the end strawn. Because if you were to pull at an angle, you can actually put the lap shear specimen to a mode of cleavage, which we don't want to do. We want to have this as close to perfect shear as possible. So, and we have completed this test for the first and second resin. So I will show you some graphs that I've made. This is 2 graphs that show the shear force of the lap shear test that they were able to withstand versus the ounce of resin per square inch on the strands that we actually saw. So one thing that we were trying to find a correlation with, of course, whenever we tested these in shear, we noticed, oh, these are not having similar strength performance properties. The 13,000 RPMs is holding much less load, but this is estimated, or this is expected to be because of the weight of adhesive on the strand. Because when you're atomizing adhesives at a faster RPM, you're going to get much smaller droplets, which will tend to linger in the air longer, or it could be spraying in a different direction than where we have this fixed location within the drum. And you can get different weights of the adhesive on the strand. So, and as you can see between the graphs of the Southern Yellow Pine and the Aspen shear test, there tends to be a correlation in the strength with the actual mass of adhesive on each strand and the strength performance that it has. So, and these are also this is the second resin. The previous slides were the first resin with the lower molecular weight. And we see a similar trend here. We had a little bit more variation in this test. So, and it'll be much more interesting to see how the correlation occurs with the third resin that we will be doing soon. So now I will move on to, I'm going to admit someone from the waiting room really quick. So now I will move on to our strand board testing. This is the primary part of the project. We are making a lot of strand board for this project to determine its actual performance characteristics. And once again, just like the lap shear test, we're doing Aspen and Southern Yellow Pine, 3 different atomizer speeds, and 3 different molecular weights of adhesive. And we're performing all the same tests to see how this all affects the strength performance of our strand board. I can't change slides now. Let's see, there we go. So this is an overview of our press schedule, which I will explain in a second. On the left side of the screen, you can see what a mat looks like going into the hot press and what it comes out looking like after it has been hot pressed. So you can see the thickness significantly goes down. So that is a good thing. So I'll go over a few main takeaways that I'd like for you all to know from this graph. Our target density of our strand board is 40.6 pounds per cubic feet. We decided on this just based on literature review and what OSB manufacturers make their strand board to, just on their different densities for their products with similar species. We press this to 0.51 inches thick, and each of these boards is roughly 16 by 16 inches. You cannot get it a perfect 16 by 16 inches because it has a little bit of squeeze out. And for the actual press schedule, just as a simplified version, the main part of this press is pressing it for 6 minutes at 200 degrees C. And for some of you who know a lot about OSB, you may think that that is a long time. You know, usually you might only need to press it for like 3 minutes. Well, just based on preliminary studies, whenever we pressed it at this same temperature of 200 degrees C for lower times, we had a lot of bond line failure in the middle of the OSB itself. So we did 2 different types of testing on our strand board. We did internal bond testing and 3rd-point bending test. This is a little diagram that I made to describe how we cut up our strand board for testing. We take out 10 internal bond specimens and then 3 3-point bending tests. So, and we, like I said previously, there's a little bit of squeeze out on the edge of the strand board. This is why we have this perimeter of unusable material, just so we don't get parts of the board that are low in density and don't meet the performance requirements that we need and the average density that we are looking for whenever testing. So for the strand board testing with the internal bond test, this is the Aspen strands. Just like I said, let me turn the lights back on really quick. There they go. So these are the Aspen tests. I would like for take a moment to kind of look at the color scheme. This will be a repeating theme whenever I show you other tests in the future. The So you'll notice there will be blue, red, and yellow. The darker color will be the first adhesive, and the lighter color will be the second adhesive, and these will be for the same RPM speed. So when you're looking at the graph and you see blue beside blue, and you see, like, for example, the dark blue next to the light blue, the dark blue is going to be the first molecular weight of adhesive, resin 1, and the light blue is going to be the second molecular weight of adhesive, resin 2, for the same wood species and same atomizer speed. So as we can see, based on the box and whisker plots, the tension in pound-feet on the internal bonds testing seem to be either on par with the first resin as it was for a second resin, or seem to be less. So, and we also noticed this trend in the southern yellow pine for the internal bond test. It seems as if the second resin performed not as well as the first. So, and when we were testing our third ones, this is something we did not do the first time, we were going to measure the mass of the internal bond specimens before testing so we can do a correction for density of all of our test samples. So those are the internal bond tests. Now I'm going to move over to the 3-point bending test. This was over a span of 14 inches. And if you are familiar with ASTM D1037, it is supposed to be over a span that is 24 times the thickness of the panel itself. And you might be thinking, oh, that should be 12 inches, you know, because you pressed it to half an inch. Well, after pressing, the board likes to spring back a little bit. So they actually ended up being a little bit thicker than we pressed them to. So, and for this, we adjusted the span of our 3-point bending test. So, and just like the same trend that we saw in the internal bonds testing, it appears as if the first adhesive performed better most of the time for the southern yellow pine and for the aspen in the 3-point bending test. So this was a very interesting find. So yes, so yeah, I just wanted to go over that really quick. So now I'm going to move on to the fourth and final part of our project, which is the resin distribution image analysis, which kind of ties everything together. With the different molecular weights, you're going to get different viscosities of adhesive, as we saw in the initial part of the project. And that can affect how the adhesive is atomized during OSB blending. You can get different droplet sizes and different droplet distributions. So we wanted to observe if there is any correlation that can be made between the droplet size of adhesive on the strands for not only the lap shear test, but also for the strand board manufacturing process, and determine how this had an effect on the composite performance. So I'll kind of describe where we pulled samples from really quick and how we did this. So like I said, during the lap shear test, we had 3 wood strands that we were spraying at once, 2 for the lap shear test and 1 for image analysis. This is where that's going to come back. So for every single lap shear test that we've done, it has a corresponding image analysis that has been done on a 3rd strand. And for the OSB strand, or the strand board that we actually made, after blending and before we pressed the panels, we went into the blender and selected strands out of there. Not like very specific selection, but they just had to be a certain size that we could take a large enough photo of. So this was as unbiased as it could possibly be. So we went into the blender and we pulled strands. We pulled 5. We're going to go back and actually take photos of both sides of these strands just to increase the amount of data that we have. So for every blender run that we did, we went and pulled 5 strands out of to do an image analysis on. And how we did the image analysis was using a laser scanning microscope. And this is a super cool device. Not only can you get a very broad image, but you can also get a 3D topography of the surface that you were analyzing. So if you will look on the left side of the screen at the very top, there is a raw image of a southern yellow pine strand that we pulled from the blender. And you can see all those little brown specks on there. That is drops of PF resin. So that's very cool. And below that, you can see the 3D surface of it. Some of the larger resin droplets will stick out and you can see them, but a lot of the tiny ones, which are also very important to consider for our image analysis and our resin distribution, aren't able to be seen during or on the 3D surface. This photo on the right side of the screen is a zoomed in section of the image on the left. So as you can see in comparison of the raw image to the 3D topography, you can look and kind of pick out some of the droplets themselves, but this isn't a reliable way to actually find out where each droplet is and do a perfect image analysis on it to determine the resin coverage. So for that, we use the software ImageJ. This is an image analysis software. It's pretty nifty. So what we can do is we can import a raw photo into ImageJ. We can turn that into black and white, and then we can determine a threshold for the color of the image. And from there, we can actually analyze the amount of area coverage for this specific distribution. So as you can see, this is an example that I currently have on the screen. We took the raw image, made it black and white, and then we did the threshold so it only shows the resin droplets. This is over a 1 by 1 inch area, and we had a 14.8% resin coverage. So some pretty exciting stuff. And we do this for all of our blender strands and all of our lap shear strands. So like I previously said, we only had 5 samples for each of our blender runs that we did, and we're going to go back and double side those so we have some more data, because as you can see, we had some highly variable, relatively inconsistent data with this. Just the trends where the only thing that we can really kind of see from this is that there was a higher area coverage on the first resin than there was the second resin, but there's too much variation. So we're going to go back and do some more analysis on this. With the third resin that we are going to be soon testing and making, well, I've already made the strand boards for the third resin, and I pulled much more strands out of the blender. So hopefully we can do some more analysis on that and see if we can clear up some of the variation and find out a little bit more about how the adhesive is distributed throughout the blender drum. So, and this is so this slide is now the resin distribution for the lap shear strands. This was very interesting, also highly variable. So, but this is one thing that was kind of expected. We didn't really need to necessarily draw a correlation for the area distribution for the lap shear strands because we have very individual data for each of them. If you remember way back to when I was actually describing the lap shear test itself, there was a lot of variability from the weight of adhesive on each sample, even between the same spray patterns and same adhesive. So, and this is some things that is a little bit out of our control, but with this data, if it has a high amount of weight or a high amount of massive resin on it, and it also had a higher resin distribution coverage, we can look at that for its just face value of comparing different strands, not necessarily on their atomizer speed that they were sprayed with, but the amount of adhesive and the resin distribution pattern. And we're going to be doing some very in-depth statistical analysis. For the lap shear strands, I've briefly talked with Ariel. I'm sure all of you who have done some typing on your thesis are familiar with her as the statistics guru. So, and we've talked about figuring out how to do a two-way ANOVA for our lap shear testing. So we are going to do a deep dive and try to solve the mystery behind what affects the bond line performance of our lap shear test and our strand board testing. So if I'm not mistaken, that is all that I had to share with you all today. So if you guys have any questions, I'd love to hear them.
Thank you, Dylan, very much. I think Dylan deserves a round of applause from all of you right now. And think of questions, either unmute and ask them directly or send them through the chat box if you're too shy to speak up.
I'm going to try to make my view of you all a little bit bigger so I can see if anyone's raising their hands.
Mm-hmm. So I do not see any questions in
this is John. I can ask a question.
Very good. Go ahead, John.
I'll ask a question. How did you decide where the threshold was when you did the thresholding?
So whenever you load an image into ImageJ, it has an automatic threshold that it sets it to, and it gives you a graph of the color spectrum for the image itself. So you can see where there are significant changes from light to dark areas on the photo. And mostly I will go off of what ImageJ automatically recommends. But if I'm looking at the image myself, I will make small adjustments to, like for example, this might clear it up a little bit. Whenever I'm doing Southern Yellow Pine for my image analysis, sometimes the late wood will have a very dark color that is close to the actual color of cured PF. But there still is a bit of a discrepancy between the color, and it's a very fine line, and you can adjust that to where it won't pick up the actual growth rings in the wood, but only the adhesive. So it's very simple on the aspen, and it's a very clear cutoff where the color contrast is. But on the Southern Yellow Pine, I have to do a little bit of adjusting myself. But for the most part, I just do whatever ImageJ recommends automatically.
So would it mean that each slide would have the threshold in different place?
It does.
Do you record these threshold values for resolving some discrepancies later on?
I do not, but that's something I can always do if it's necessary.
Mm-hmm. Nice.
Yeah, I was going to ask about that, if how different the threshold values are and whether they're small enough to just be from outside sources of any differences in the world around when the photo was taken.
It's not significantly different, and there is a little bit of variation, but like I said, whenever you load an image into ImageJ and you do the threshold, it's going to give you a graph of the different amounts of each specific color and based on light to dark. And there's always a clear ramp where the color changes from the actual shade of the wood to the phenol formaldehyde resin. So it's always pretty easy to pick out that jump and be able to set it where, and if you're moving along the actual ramp of where the adhesive chain or the adhesive color and the wood color meet, you're not going to get a lot of difference in the actual imagery that's picking up. So you have a little bit of safety room within there, if that makes sense.
Okay, cool.
Nice. Other questions?
I would like to ask a question. Did you see from your preliminary results, did you see any signs for effects in your research yet on the bond performance?
So from what I have done so far, and we have not drawn any conclusions yet on our project because we have not done the full-blown statistical analysis, but just from my view itself, it appears that the highest RPM with the lowest molecular weight has shown the strongest performance properties, which was very interesting because I didn't expect this until after testing. Whenever I did preliminary studies and I was making strand board and then doing image analysis on it, I would look at the 13,000 RPM blender strands, and it would be very, very tiny resin droplets, but they would be spread out all over the strand. And when I was looking at the 7,000 RPMs, it would be much larger resin droplets over a smaller area itself. So I was almost expecting that the 7,000 would be the strongest, but then after testing, it turned out 13,000 RPMs, I think actually does get the best distribution of resin across all the strands. But having said that, we have not concluded anything yet, but that is just what I think so far.
So Dylan, I have a question. Are you familiar with the notion of the resin efficiency? This is the amount of resin that provides similar shear properties on the same kind of strands.
So I'm not familiar with the resin efficiency, but if this does clarify, whenever doing strand board testing, we have a very specific amount of adhesive that we use for making all of our boards, and that does not change across anything.
So there is a theory developed since 60s, I think, since the spinning, perhaps later, since the spinning disk atomizers have been used, and there is some science behind the smaller droplets allowing you to achieve the same strength of the shear bond of the bond with less resin, just because of much better distribution of the droplets on the surfaces.
Well, hopefully that's something we might be able to see within our shear testing, because like I said, we're recording the actual weight that we estimate that is falling onto each individual strand. We can't go and weigh each individual strand, but by having that piece of aluminum, we kind of get a window into what might possibly be happening to all the other adjacent strands. And from the graphs, there was a very clear trend of the strength performance to the mass of resin on each strand. And of course, that was kind of expected. More adhesive, better bond line performance. But with our higher RPMs, maybe once we equalize the amount of weight to the actual bond line performance, we might see that the smaller droplet size, larger area coverage, as opposed to larger droplet size, smaller area coverage, might actually be the most efficient way.
So I have a question. How do the droplet distributions on the strands that you pull from the blender for making your panels, where you have much more of the strands in the blender interacting with each
Absolutely.
other? And so on. How does this droplet, and being there for period of time, how does this droplet distribution compare with the distribution on the lap shear strands, where you have these droplets exposed in a very different way for a very short time?
Yes.
And just individual. Have you compared these distributions?
Yes. So we haven't done any in-depth analysis on the difference between the blender strands versus the lap shear strands. And that is one thing that's very true. I'm glad you brought that up. A big part of the resin being distributed in the OSB manufacturing process is attrition blending, with the strands rubbing together and sharing adhesive. But from our image analysis, it doesn't appear as if the adhesive is necessarily being smeared across the strands by any mean. I'll go back to this slide. This is an image from the blender itself. And we were getting very similar droplet patterns on the lap shear tests themselves. But it is different, of course. There is a bit of variation. And one of the biggest differences as well with our lap shear strands, the surface quality is as good as it gets. We specifically made these strands to have phenomenal surface quality. And if you look at these blender strands in depth, whether it's the southern yellow pine or the aspen, it appears as if once the droplet hits the strand, it's pretty secured there. Like if you actually look at Dr. Kampke's background, you can see an epifluorescent microscope slide of the phenol formaldehyde resin on what I'm guessing might be an aspen strand. You can see that the adhesive, once it hits the wood surface, it tends to travel up the pattern of the grain a little bit. It'll follow the grain orientation, so it will become longer than it is wide. So, and this is something we observed not only in the blender strands, but also on the lap shear testing. Once the adhesive hits the wood, it's going to immediately soak in. So, and this kind of secures it in place. And we saw this, or at least I've seen this in comparing the lap shear strands that we did image analysis on to our blender strands. So there is going to be a lot of variation. And then sometimes you will have a huge droplet on the blender strand because it'll fall right in front of the spray of the atomizer and it will get caked. So you do have those differences, but that's why we are going to increase our population sample size for this third resin to see if we can clear up some of the variability.
So the aim of my question was, how representative are those very tightly controlled lap shear specimens with the how representative they are compared to what you actually get from the blender in lab or even industrial conditions?
I would say it's a good representation. Looking at the raw photos side by side, with aside of the grain pattern and the surface quality, it's almost difficult to tell the distribution patterns apart. They're very similar. They're not exactly similar. The lap shear strands, of course, are much more uniform and have less variability, but we are getting very similar distribution patterns on the blender strands that we are getting to the lap shear strands. This is actually why we took the time that the lap shear strands were exposed to from the atomizer spray from 30 seconds to 10 seconds, because at 10 seconds, it almost mirrors the distribution pattern that we are seeing from pulling blender strands. Mm-hmm. So we spent a lot of time in the preliminary testing trying to get this as close to representing a blender strand as possible. So, and like I said, with no attrition blending, being at a fixed location, it's not going to be perfect, but it is very similar, and we are in the ballpark of the amount of area coverage of adhesive on the strands with our lap shear strands to what you would see from pulling an OSB strand from the blender.
Okay, very good. Other questions, my friends? Other questions to Dylan?
I'll ask another question. Have you done the calculation to see how many for resin 3, how many samples you need to get statistical significance, and what's that number?
For our blender strands that we'll be pulling, we're taking 30 images.
Is that what the calculation said?
That's what Dr. Kampke and I discussed and agreed on.
Oh,
so
okay.
I wouldn't say the calculation, but the brainstorming session concluded that.
Okay, other questions to Dylan regarding this presentation or life at large? Because why not? If there are none, I would like to thank Dylan again for this exciting presentation and to wish him good luck in the final stage of his project towards the defense. When do you plan your defense?
It's a good question. We're working on that.
Very good. Not immediately, right? It's not.
Yeah, we will see. We will see. Might have to maybe push into summer a little bit, but I am working my buns off to try and get this done this term. So, but we got a lot of work ahead of us, and I got a lot of writing to do. So we will see. And I know you guys love having me around. So.
Yes, we do. So. As soon as the date is known, it will be posted, and I'm sure most of us will attend and just see
absolutely
the shape of this project.
Oh yes, yeah. I expect to see all of you here, all 30 of you here for my defense as well. So yeah, but hey, thank you guys for taking the time to listen to me today. It was fun to get present live again. I missed this, so yeah.
Very nice. It's nice seeing you live as well.
Yeah.
We start forgetting how people look like, really.
Oh yeah, I cut all my hair off, if anyone noticed that.
Okay, final round for applause for Dylan. Thank you very much all for attending.
Good job, Dylan.
See you next week.
Thank you.